So we've been talking about power series for a while now, but do we really understand what they're doing for us? Right, so remember our basic one, and that is 1 over 1 minus x can be represented by the power series x to the n from 0 to infinity, as long as that x value is less than, the absolute value is less than 1, so between plus or minus 1. Okay, so remember this relates to a geometric series if that constant ratio is less than 1, right? You get the infinite sum, so you can go back and look at geometric series if you need to review that. So if we just write out the first few terms, what this says, right, that is that 1 over 1 minus x can be represented by, so if n is 0, I get x to the 0, that's 1. If x is 1, or I'm sorry, if n is 1, I get x to the first. If n is 2, I get x squared, right? And I'm just going to keep writing for a while. And now I'm tired. So plus dot, 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 because it goes to infinity. So look at what this says, right? I am essentially saying that the fraction 1 over 1 minus x can be represented by this polynomial, this power series, as long as you are close to, right, well, close to 0, right, for, right, negative 1 to 1. Okay? And you might think, oh, well, gosh, that's cool. How many of these do I have to write? Do I have to do infinity of them, right? And as you might guess, the more you do, the more accurate you become. So I have my calculator here, and I've already plugged in. Let me zoom down so you can maybe see it better. I already have, right, the 1 over 1 minus x in. Okay. So let's go ahead and put in some of those terms until we get tired of the power series. So 1 plus x squared plus x to the third plus x to the fourth. I'm almost tired, plus x to the fifth. Okay, I'll show you my window real quick. Grab a screenshot if you need to. It's pretty small, right? Because I'm only interested in those x's between plus or minus 1. I just like to have a little buffer. Okay. Oh, that's a weird kind of image on my calculator screen. Oh, well. So go ahead and take a look at the graph. So this first one is the rational function. So 1 over 1 minus x. Right, you've got that vertical asymptote. Oh, here comes our power series. Look how that red line is just hugging my rational function line for those x values between, right, plus or minus 1. Now you can see that at negative 1, I'm a little bit off, and at positive 1, right, we start getting off again. So let's go ahead and let's go back to our y equals screen, and let's put in a few more terms. And let's see how much closer it's going to get. So I'm just adding in, let's do 3 more, plus x to the 8th. There's the rational again, and here comes the power series. The red line should be a little bit closer for a little bit longer. Oh, it's getting slowed down. Oh my gosh, and see, do you see how much better it is when we added in those 3 terms? Okay, so that is right. The power series is giving us a nice polynomial representation of something, right, that's not very nice. And the reason why polynomials are nice, right, is it's multiplying and adding, right, or essentially, right, adding. And adding is super easy to do, especially for computers. Okay, so if, right, my function can be represented by this set of power series and they look the same, right, the graphs look the same, then, I'm going to zoom all the way back out, we would expect, right, the slopes of the tangent lines to also be the same. So if we so f of x being played by whatever function that we have, in this case it's our rational function, if f of x can be represented by this very generic power series, right, so you might have a leading term, and it might not be centered at 0, so x minus c to the n. So f of x, our function, we found a power series that will represent it. And if we, right, assume that it has a non-zero radius of convergence, even infinity, that's okay, right? It could converge everywhere. It means the power series and the function match up everywhere, not just on that little chunk that we've been talking about. plus or minus 1 for the one that I've been using, or, right, C, if you centered it at some other x value, plus or minus r, that radius of convergence, then we can find, or then f is differentiable on that same, right, interval of convergence, and we can find the derivative of f, right, of that rational function or whatever it is we have by differentiating the power series. Okay? And so what that looks like, right, if you look at your power series here, and if you think about just using the power rule of differentiation, right, the exponent comes down, x minus c to the n minus 1, there it is, derivative of what's inside, but because it's just, right, x minus c, that derivative is 1, so I don't have to worry about that. So we can find f prime, right, by taking that derivative. So let's go ahead and do that for the one that we've been looking at. So I'm going to go ahead and scroll back up. So we're going to find, so on this one, right, f of x is 1 over 1 minus x. Okay, and we can find f prime using our derivative rules. Right, so I'm doing it both ways. So I'm going to do it one way using our Calc 1 strategies, and then I'm going to find it another way by differentiating that power series. Okay, so f prime of x, so I would think of x as, right, 1 minus x to the negative 1. So the power rule says the negative 1 comes down, negative 1, x minus hold on, let me get my white out. Distracted by my dog with his toy behind me. Oh, hold on. He's got something that's not his. Sorry, choking hazard. Okay, so the negative 1 comes down, 1 minus x to the, take 1 away, negative 2. So now I am going to do derivative of what's inside because it's 1 minus x, so I've got that extra negative 1, so times the negative 1, that'll make that positive. So my f prime will be 1 over 1 minus x squared, right? Okay, so there it is doing it, right, just looking at our function. Now let's find it by using, right, so I'm looking right here, we're going to differentiate the right side. So this is the derivative of the left side. Let's find it using the derivative of the right side. Okay, so the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x plus 3x squared plus 4x cubed plus 5x to the 4th plus, right, dot, dot, dot. So let's go ahead and I'm going to grab my calculator again, and let's plug both of those in. So I'm going to go ahead and I'm going to unselect these by using, right, being on the equal sign and hitting enter. So in my y sub 3 screen, I'm going to put my, my left side, so 1 over 1 minus x squared, quantity squared. And then in y4, I'm going to type that derivative of the power series. So I'll have 1 plus 2x plus 3x squared plus 4x to the 3rd plus 5x to the 4th. Okay, I'm tired already. Okay, so now let's just graph those two. It has the same interval of convergence, so I'm not going to change my window at all. Right, and there comes that power series in purple, and I can't really see the color on the screen, but, do you see how it's lining up there? And it's not lining up very far, so I would need to put in a few more terms on my power series to actually get it. But you can see, right, the derivative of the function itself and the derivative of the power series, the same, or close enough. So if we can differentiate, right, you know what we also can do? We can also integrate, which again is going to make sense because, right, if the graphs are matching up, then I would assume, right, it would make sense that the areas beneath the curves, if the curves are the same, it would make this, right, sense that the areas are also the same. So, right, if the integral of the function, to get that, we can integrate, and you can see, right, I've just written the integral here with the power rule, right? So it was x minus c to the n, so we add 1, divide by the new, we're still summing, and then we have a constant. Oh, before I go away, I want to point out right here, back when we did the derivative, our we started at 1 instead of at 0, because otherwise, right, the first term would be a 0 if you started at 0, so it just takes out one extra 0 term. Okay, so here we can go ahead and start at 0 and create that new one. Okay. Now, note, the new series will have the same radius of convergence as the original series that you found. So I will leave it to you. You can go ahead and plug in your integral. So you can integrate 1 over 1 minus x, right? It's going to be a u sub. Okay, you're right. Here we go. Sorry, my phone rang and I wanted to grab it, but I won't. So if we want to integrate 1 over 1 minus x dx, okay, I'll do this side. You guys can integrate the power series one, right? So that is, we're integrating u to the negative 1, and then I'll have a negative out here, du, right, if you do a little u sub. So that's going to be negative natural log of u, 1 minus x, plus, right, your constant. So, oh, there's something to think about. When you plot this, okay, you're right, here we go. So y equals, so now I'm going to get rid of these guys. And let's go ahead and, I know, I can never stop. So we're going to do that one. So I will have a negative natural log of 1 minus x. And then we're just going to integrate on the fly, right, as we go. So we're going to go term by term. So if we integrate 1, we'll get x. If we integrate x, we'll get x squared over 2. And then we'll get x cubed over 3. And then, right, I'm just adding all these up, x to the 4th over 4. Last one I'll do, and then I'm going to be tired, x to the 5th over 5. Okay, they can be off by a constant, which means you can have a vertical shift and it's still legitimate. So here comes my, what was that one? Oh, look, and it doesn't even have a vertical shift. It's matching up exactly. Oh, 1 over 1 minus, that's why. I was expecting a natural log graph, and I forgot that 1 minus x. That's why it's flipped and shifted. Okay, so power series. You can integrate term by term, you can differentiate term by term, and you will get the integral or the differentiation of the original series.